Today, I want to talk about the integral test, which is one of my favorite tests, actually, just because I'm a fan of integrating. And instead of me giving you a really rigorous proof for the integral test, I encourage you to actually watch the video, and I'll link it in the description below from Khan Academy. And Sal Khan over there does a great job of giving you an intuition for why the integral test works. And I won't recap everything. I encourage you to go there and watch it if you're so curious. Actually, I encourage everyone to watch it. But to kind of recap or summarize what's being said here is if we were to take a series like 1 over n squared, which looks like the following here. Let me just write out those terms. So if we look at a series like 1 over n squared here, what we can effectively do is reason the following. If we can think of an equivalent function, a function that models something like 1 over n squared with the following conditions, that this function is positive, it's continuous, and decreasing, and if you look at 1 over x squared or 1 over n squared, we see that all three of those conditions are met. And if we look at the integral of that function, which graphically means we're looking at the area underneath its curve, we see that the area underneath this curve, which is highlighted in yellow here, is certainly going to be finite. If we think about this as an improper integral, because it is, we see that the area underneath that curve, or the area underneath this function, converges to a finite value. And from 1 to infinity, we see that that finite value is 1, and I've written out the improper integral below. But what we see here is, look, if this yellow shaded region over here does indeed converge to a finite value, and if my original series that I have here, and notice that these terms here are represented by these areas, 1, 1/4, 1/9, well, the highlighted area underneath the curve is certainly going to be greater than the sum of these terms here. In other words, the sum of these terms are an under approximation for the actual area underneath this curve. And if the area underneath this curve is convergent to a finite value, then these terms, the sum of these terms up here, must also be convergent to a finite value. There's no way that something that is larger that can converge to a finite value while having an under approximation of that somehow suddenly diverge. That's just not possible, right? Using this comparison test, we can see that if the over approximation converges, the under approximation, or the smaller value, must also similarly converge. So the integral test says if your function is positive, continuous, and decreasing, then your series is going to behave the same way that your integral, or its corresponding integral of that function, would as well. They may not necessarily converge to the same value, but they will both either converge or both diverge. So again, I encourage you to watch that video. It does a much better job of articulating this reasoning here, but hopefully that makes sense to you. And if you've done that, now let's go ahead and let's actually just try a couple of quick problems with this. I'm going to just do the first two because I think the rest you can actually use either the integral test or the P-series test, which I'll discuss in the next video. So let's try something like number 1, which is a pretty similar problem here. So we look at this, and first off, ask yourself, is this series representing a function that is positive, continuous, and decreasing? Well, since our lower index starts at 1, we know all of our terms are indeed going to be positive. Well, next up, are my terms going to be, or does this function here represent a continuous function? Well, yes, the domain for that function would be all real numbers, so there aren't going to be any discontinuities. We know it is a continuous function. And next up, finally, is this function here going to be decreasing? Well, yes, as our denominator gets larger and larger, its overall ratio of the terms are going to get smaller and smaller. So it is indeed decreasing. We know that. Well, if these conditions are true, then we can apply the integral test, which is to set up the integral of a corresponding function. So we would have to use an improper integral since one of the bounds is infinity. So we'd say, let's look at the limit as a approaches infinity of an integral from 1 to a of 1 over x squared plus 1 dx. Well, what is the integral of this? It is arctangent. So let's write the limit as a approaches infinity of the arctangent of x evaluated from 1 to a We'll rewrite that from 1 to a. And then once we evaluate that integral at those bounds, we would say this would be arctangent of a minus arctangent of 1. Now, here's a little bit of quick inverse trigonometry review. So, for what angle would the tangent produce a value that is approaching infinity? Well, that would occur at pi over 2. Well, what is the arctangent of 1? Well, I know that tangent of pi over 4 gives me 1, so this would be minus pi over 4. So pi over 2 minus pi over 4 is pi over 4. So what are we saying here? We're saying that this integral, which is an over approximation for the sum of the terms of the series, does indeed converge to pi over 4. Since my integral converges, and it's larger than the sum of my actual series, then my series also has to converge. So I would say, therefore, this series converges by the integral test. And I'm just going to write IT for short, but you know what I'm saying, right? So this series does indeed converge by the integral test. Does it also converge to pi over 4? Not necessarily. That's not something that we can conclude, but we can conclude that it will also converge. Okay? All right, let's go ahead and try one more example in this video. So let's try something like number 2. So for number 2, let's first check to make sure that we can indeed use the integral test. We know that this function is positive because n starts at 2, so all my terms are going to produce positive outputs. So it is positive. Is it continuous? Well, we have some danger here. We have an n and a natural log of n here, but those discontinuities would occur at n is equal to 0, because that would cause this to be equal to 0. And when n is equal to 1, because the natural log of 1 would be equal to 0. But fortunately for us, our lower index starts at 2. So given where the lower index is, we can say that this function is continuous. And then finally, is this function decreasing? Well, yeah, our denominator is going to increase without bounds, so our terms are going to indeed get smaller. So we can say that this function is decreasing. So we can move on and write our improper integral. So we can apply the integral test. So let's look at this. This would be the following. From 2 to a of 1 over x times the natural log of x dx. Well, it looks like we're going to have to use u substitution here. We can say, all right, if our u is equal to the natural log of x, and the derivative of that is 1 over x dx, and we can unhook the chain here, so we can say the following. We can say that the limit as a approaches infinity would be the natural log of the absolute value of u. And what is u? It's the natural log of x. And we're evaluating this from 2 to a. So let's write this out now that we're evaluating it, our limit at those terms. So we have a natural log of the absolute value of natural log of a minus natural log of the absolute value of natural log of 2. Now let's take a look at this limit here. What's going on here? Well, we work inside out. The natural log of a, as a approaches infinity, the limit of that is going to approach infinity. And again, the limit of the natural log of something that's approaching infinity, all of this here is going to approach infinity. This limit doesn't exist because this approaches infinity. So what can we say about this integral then? This integral diverges. And since we see something here that is an over approximation here, our series is also going to behave the same way. This series also diverges by the integral test. Okay, so hopefully this helps give you a sense of how the integral test works. And in the next video, we'll look at some of these other problems here, but we'll give ourselves the option of using either the integral test or something called the p-series test.